Today, we are diving into a really fundamental shift in how we're building intelligent machines. We're going to move beyond just teaching an AI what to know and into the far more fascinating territory of teaching it how to think. So let's start with a puzzle, one that you have probably run into yourself. We've got these incredible language models, right? They can write beautiful poetry, they can summarize dense academic papers, they can even write pretty decent code. They feel so knowledgeable. And yet, you can ask one a seemingly simple logic puzzle, and it'll confidently spit out an answer that is just plain wrong. Or maybe it gets stuck overthinking a really basic question, just spinning its wheels for paragraphs when all you needed was a simple yes or no. So what is going on here? And that question, it gets right to the heart of the problem. You know that gap you feel between a really slick demo and a system you can actually rely on for something important? Well, that gap isn't about the model not having enough facts crammed into it. The real challenge, the frontier, is engineering the process of reasoning itself. It's about evolving from a vast static library of information into a dynamic, flexible cognitive toolkit.
Okay, so to really wrap our heads around this, we've got to go back to first principles. Let's ask a really basic question. What does thinking even mean for a large language model? How does it actually get from the prompt you give it to the answer it gives back?
Well, at its core, a model can take one of two paths. The first is what you could call a reflexive answer. It's that single-pass, gut reaction response. The model reads your prompt and immediately generates what it thinks the answer is, based on all the patterns it's learned. But the real breakthrough came when researchers figured out how to teach models a second mode, deliberate reasoning. And the key, it turned out, was getting them to show their work. And this is the whole idea behind chain-of-thought prompting. Instead of just asking for the final answer, you prompt the model to break the problem down to think it through step by step. It's exactly like how you or I might grab a scratch pad to methodically work through a tricky math problem. This deceptively simple shift created a kind of cognitive workspace for the model, and it completely unlocked its ability to tackle way more complex reasoning tasks.
Now, the success of this was so dramatic that it led to this very seductive and, I gotta say, very common belief in the field, that the answer to any reasoning failure is just more scale. Just build bigger models, throw more parameters at them, feed them more training data. The assumption was that if we just make everything bigger, all these pesky reasoning problems will just disappear.
But the data tells a very different story. It turns out that as you scale, performance on these complex reasoning tasks gets better for a while, but then it starts to plateau. You hit a wall. And this reveals a crucial insight. The real bottleneck isn't just what the model knows, all that stored knowledge. It's the computational process it uses to think. It's the actual computation that happens in the moment when you ask it a question. That's what we call inference time.
So if just making models bigger and bigger isn't the whole answer, then what is? Well, this question brings us to a new and really powerful idea that's starting to reshape how we build these systems. It's about getting much more deliberate about how we design the thinking process itself.
This new paradigm has a name, Cognition Engineering, and it's a huge shift in focus. Instead of putting all our effort into cramming more and more knowledge into a model during its training, we are now systematically designing and scaling the computational process it uses to think at the very moment it needs to solve a problem. It's a move from being an architect of a library to being an architect of thought itself.
And the main tool we use for this is a practice called test time scaling. You can think of it like giving the model a budget of time and computation to think harder whenever it hits a difficult problem. So instead of forcing it to give one quick answer, we allow it to spend those resources to explore, to reason, and to refine its solution. And once you give it that budget, you unlock this whole new set of really powerful cognitive tools. You can get the AI to brainstorm multiple different lines of attack on a problem all at once. That's parallel sampling. You can have it explore a branching maze of possibilities, kind of like a chess grandmaster using tree search. And you can even teach it to do something that feels deeply human, engage in self-critique, and revise its own work. All right, let's make this more concrete. And this is where it gets a little counterintuitive. Surprisingly, one of the most powerful ways to engineer better thinking isn't about adding more complexity at all. It's about taking things away. It's about teaching an AI what to ignore. This is based on a fascinating idea called the information bottleneck principle. The whole concept is to force the model to create a compressed, almost minimalist representation of the problem it's trying to solve. It has to learn to throw away all the irrelevant details, all the noise, and focus only on the information that is absolutely critical to the task. It's like a pilot trying to land a plane in a storm. They're not looking at the color of the clouds or the landscape below. They are focused only on the handful of critical instruments they need to fly the plane safely. So, researchers decided to put this exact idea to the test. They took an AI that was designed to solve a really gnarly logistics problem, planning the most efficient delivery routes for a whole fleet of vehicles. Then, they applied this information bottleneck, basically forcing the AI to ignore all the distracting data and focus only on the variables that were absolutely essential for finding the best route. And the results were pretty incredible. Just look at this. For the traveling salesman problem with 200 cities, performance didn't just get a little better, it jumped by over 270%. That is a staggering improvement. Across the board, forcing the model to think less, to focus only on what truly mattered, made its decisions dramatically smarter and more efficient. Okay, but what happens when a problem actually requires more thinking, not less? What if the best way to solve something isn't a strategy we can easily program into it? Well, this is where cognition engineering gets really exciting. This is when the AI starts to discover entirely new ways to reason, all on its own. We can enable this using a technique called reinforcement learning. The basic idea is you give the model a goal, like, say, solving a really hard math problem, but you don't tell it how to do it. You just let it try over and over again, and you reward it when it gets the right answer. And through this massive process of trial and error, it doesn't just learn facts, it autonomously discovers and refines entirely new effective reasoning strategies. And this isn't just theory. Models trained this way are now getting top scores in elite math competitions and hitting human competitive levels on programming platforms. And sometimes the strategies these AI systems discover are completely alien. They genuinely surprise their own creators. It really is reminiscent of AlphaGo's famous Move 37 against Lee Sedol, a move that human Go masters thought was a terrible mistake, right up until the moment they realized it was absolutely brilliant. We are starting to see AI develop cognitive pathways that are incredibly effective, but in ways a human might never have even considered. Okay, so let's pull all this together. What are the crucial points to take away from this whole paradigm shift? How should this change the way we think about building and using these intelligent systems? Let's try to distill it down into a few core mental models. The first big mental model to adopt is this. Stop thinking of inference as a single instantaneous event. You ask a question, you get an answer. Instead, start seeing it as a controllable search process. You, as the engineer, are guiding the model through a vast space of possible reasoning paths, and you have the power to design how that search happens. Second, reinforcement learning is not just for playing video games. It is one of the most powerful tools we have for letting an AI autonomously discover and master new cognitive abilities. It's how we make the leap from teaching AI what we already know to letting it discover what we don't. And third, never forget the power of that counterintuitive lesson we just saw. Sometimes the path to smarter, more robust decisions isn't about more computation, it's about intelligent compression. Better thinking can often mean being better at ignoring the noise. And all of this leaves us with one final and kind of provocative thought to chew on. We are, without a doubt, entering a new era of intelligence symbiosis, where we can actually learn from the cognitive strategies our AIs discover. But it opens up a pretty profound question for the future. As we teach machines to reason in ways that go beyond our own intuition, what happens when their thinking becomes so effective, yet so utterly alien, that we can no longer follow their logic at all?